The next speaker is Konstantinos Spiliopoulos, who has slightly changed the title into Large Deviations and Monte Carlo Methods for Problems with Multiple Scales. Please.
First of all, thank you very much for the invitation and for organizing this. It's been very nice. The essence is the same of the talk. Given the plurality of the audience, I decided to give an overview of some of the results in the session.
Your mic on.
Better?
Better?
Yes.
Better. So I was saying that given the given mix of the audience, I decided to give more of an overview talk of different results in this area, since it seems to be a little bit different than the majority of the talks, at least in this workshop. The motivation for this was to understand large deviations and rare events and Monte Carlo methods when you have multiple time scales in a problem, and then how to use the theory in order to develop algorithms for that. And what are the problems and what are the issues that come up, both because of the rarity of the events, but also because of the multiple scales that are involved in the problem at hand. Now, instead of going through the outline, let me just go directly to the point. So, this is how a typical smooth landscape would look, and this is how a typical rough scape would look. And this is more closer to reality than this, in the sense that you do have very small energy barriers within the big wells, let's say. And people have studied questions of this sort for many years, and I will have a literature review in a minute. So what we try to understand is, first of all, how to use large deviations theory to accelerate convergence, and also how to take this structure into account, if possible. Now, the goal of this research program is to be able to compute exit probabilities and transition probabilities, to be able to take into account the roughness of the energy landscape, which introduces a multiscale effect, and to understand the interaction between the multiple scales and how rare the event is, and to design Monte Carlo methods based on that. And there are difficulties here that I will come to the end, and there are many folklores in the community which some of them have proven to be correct, some of them have proven to be incorrect, so I will comment about this. So there are issues because of state dependence, multiple scales, and rest points. And the point is that if you have multiple scales, then closed form formulas as Ehring-Kramer's formula are not available anymore. So you need simulation. So the question was, can techniques like averaging and homogenization help to address these issues? So as an example, a typical example that people have, a typical equation model that people have written down is what is usually called overdamped Langevin equation, which is nothing else but gradient flow plus noise. And W here will be just Brownian noise. And so this would be like a typical V, of course, could be much more complex than just a picture. And people have studied this a lot, so there is a lot of literature in large deviations and metastability theory that I'm...
You have a department of large deviation.
Hmm?
You look at the bottom, it says there is a department of large deviation.
There is what, eh?
I know.
All right. Now, the picture that will be the only picture in my talk that will be more realistic than the others is this one, which is not by me. It's Marcus Muley gave it to me, who started working on this issue, who's in the University of Brussels. This is just to motivate discussion, and that's the question that was posed, was when you have so this was a biological organism for which I don't know much about. The issue was that the question that they asked is that if you have a transition from one energy to another energy, and if you map this appropriately, you get a landscape like this on the right-hand side. And the question was that all these little wiggles, how can you take them into account, and should you just average them out? What you should do? Now, so you can view this as a smooth function superimposed by a fast fluctuating function. So that's one observation that one can do. And actually people did this observation, and I will comment on that. So a typical model now to take into account the previous picture, meaning these wiggles, would be to consider something of the sort of the top equation, where you have an underlying profile and you superimpose on this a small but fast oscillating function. And in that way you create a slow fast dynamics where you have a slow motion and a fast motion. And then you have two small parameters to play with. One dictates the rarity of the event, which is the epsilon, and the other one dictates how fast the oscillations are, which is the delta. And it turns out that depending on the order that you take the limits, you get completely different behavior, as one would expect. So this is not so strange. Now, it turns out that doing this model and doing the mathematics correctly, as I will mention in a minute, this type of model is actually the equation in the model in green, that just a very toy, simplistic thing, was written by Zwanzig in 1988, chemist, who tried to understand these things, and he came up with some formulas which we were able to recover in the general case, in the case of regime 1. So if delta goes faster to 0 than epsilon, so if oscillations happen fast, and then you have averaging, and then you get the rare event. Now, so having said that, the goal of this research was, first of all, to understand the last deviations theory in this case. That was the first and necessary step in order to move on. And it's a way to capture essential rare event behavior. So I will comment a little bit on this. Here we used stochastic control arguments to deal with this, but the advantage of using stochastic control here was that we could also identify the control that would lead to the rare event, which we could then use in order to devise Monte Carlo methods for this. So I will comment on that as well. Now, and when it comes to importance sampling, which is one of the methods that you could implement, importance sampling, I believe that most of you here are aware, it's an acceleration technique, and there are different ones. There are splitting methods, so this is just one way to do it. It's a very popular way. And what you do in importance sampling is that you change the measure of simulation in an efficient way. Now, efficient way could mean different things. So if I want to compute the probability of an event, I could just take the law of large numbers and just count the percentage. But this, when you have rare events, this is very, very inefficient. One thing that you can do is to allow 1 degree of freedom, which is to change the measure of simulation, to simulate under a different measure, and then to control the variance of the estimator, to choose the new measure so that the second moment of the estimator is as minimum as possible. This has been developed, I think, first from the statistics community. Sigmund did most of the work in the 70s, in very different problems. And then this has been carried over to many different settings. So we try to understand how this works when you have state dependence and metastability. Now, as I will comment later on, the optimal measure of simulation that you can use is related, in theory, to Hamilton-Jacobi-Bellman equations, which are very hard to deal with this in practice. So that is why the theory of subsolutions were developed, and it amounts to it's enough to find good subsolutions, which then brings another problem into the picture, how to construct subsolutions. And which is difficult because you have state dependence, you have metastability, and you have high dimensionality. So I will come also to this in the very end of the talk. Now, because there has been a lot of work done in this general area, I decided to just put a roadmap, given that people here are not, know things in this area, but maybe not experts in this. So from last deviations theory, in the smooth case, when you don't have any fast oscillations, the problem has been very, very well understood. And there have been many people that have worked on this. Friedlin, Wenzel, Bouvier, Olivieri, Fares, Dupuy, Ellis, Fleming, and others. In the rough case, when you have oscillations, there have been some very partial results. I think the first one was by Baldi, and then Friedlin and Richard Sowers wrote a paper. Veretennikov also did some work. And there was also some work from the homogenization of stochastic
from stochastic homogenization of Hamilton-Jacobi-Bellman equations, and I have listed here some names, so mainly using PD techniques. But there was many still issues were open, so for example, all these results wouldn't cover the simple model that I mentioned, and we covered this. Then, in terms of importance sampling, there was some work in terms of the theory of importance sampling in the smooth case, but nothing in the rough case, so we addressed this point. And in terms of practical application of importance sampling, meaning how do you construct, how do you do it when you have an actual problem instead just of saying, of relying on solving equations, that was unknown in both the smooth and the rough case, so we also contributed here. And there has been many work in the applied community in chemistry and physics dealing with problems of this sort. Now, so before I lose you or you lose interest on this, these are the conclusions of the research, so now you can read this and leave the room. So, large deviations behavior, first of all, in regime 1, for example, where the oscillations go faster than the large deviations kick in, then what you get is what intuition says, meaning that you should average first and then do large deviations. The situation is obviously different in the other regimes. However, when one goes to Monte Carlo methods, it turns out that this is not the case anymore. And I will comment on this, meaning that you cannot just average and then do Monte Carlo as you would do it if it was smooth. You have to take into account the corrector, you have to take into account the pre-limit behavior, even if your goal is to achieve asymptotic optimality. So this is important that we discovered when we were working on this, and I will comment on that too. And also, it turns out that it's not trivial to construct, so as I mentioned, there is this connection with optimal change of measures and solutions of Hamilton-Jacobi-Bellman equations. This was known in the control community many decades. But it's very hard to work with these objects because, first of all, you only have viscosity solutions, and second of all, you cannot really solve them even numerically in dimension more than 4 or something. So this was totally impractical. So we came up with Dupuy, Paul Dupuy, and Wang came up with the subsolution method, which we applied here. But it's also difficult to construct subsolutions. Yes?
Like the subsampling that Pavliotis and Stewart did fall somewhere under 2?
The subsampling that they did had to do with estimation of parameters, which is a different problem. So if you have statistics, so if you have parameters in the model you want to estimate, and you have the homogenization regime, what they said is that the maximum likelihood estimator is not unbiased, so you need some sampling.
Do you also think of it as a Monte Carlo method for simulation?
Yes. So here we address this issue of how to construct subsolutions. And it turns out that, for example, this is also a take-home message that I want you to take. There is this folklore in this community that if you just follow optimal trajectories, you should be doing well with Monte Carlo. That's really not true here, and I will comment why it's not true. It's not true for many reasons, that the mathematical and practical reasons, and one has to do it in a state-dependent way that takes some things into effect that I will come to that in the end. And I have time, I think, yes. But let me give you, so let me start now this, unfolding this. So let me start first describing the large deviations theory, then the Monte Carlo theory, and then how to construct subsolutions, and then I will conclude with numerical examples. Okay, so that's the idea. Now,
you can construct many subsolutions possibly, right?
Infinitely.
But only some of them.
Only some of them. They need to have certain properties. Yes, yes. So now, in large deviations theory, the goal is to come up with what is called action functional, which is nothing else but what I have in red over there, because I'm not tall enough to reach that, so it's red, the red thing, which basically says that if you give me a deterministic trajectory, the probability that my stochastic process will follow this trajectory, deterministic trajectory in path time, will be very small, obviously, unless this is the typical path. And how small it is exponentially small, and the rate is this S of phi, and phi is the input trajectory that you give me, all right? So the goal is to compute this in large deviations theory. And if you have this, then you can characterize, at least in the logarithmic asymptotic sense, things like probability of escape from a set, or the expected value of some functional of interest. And these are the formulas that you have in the end. And this should be understood in the logarithmic sense, which means that you take the log, you multiply by epsilon, you take 0, epsilon to 0, and you get the right-hand side. For example, in the absence of fast scales, this has been very, very well developed. And I have a typo here. Ignore that sigma over there. It was just a leftover. But anyway, you can just keep it. It's OK. Just diffusion. So in the model 7, for example, the rate function it's quadratic, and it is the velocity minus the drift divided by the diffusion. So, and that's Friedel-Wenzel theory. Goes back many, many years. All right. Now, for the fast oscillation stuff, so I will just write this model down, which is the one that motivated the whole project. So you have a smooth function which is superimposed by a fast oscillating function. And then you want to study, you want to understand what is the last deviations behavior of the solution of this equation. And if you're just interested in the case that epsilon over delta goes to infinity, meaning that delta goes to 0 faster than epsilon, then the last deviations behavior is as you would expect, meaning that you would average first and then do the last deviations. Now, I have to mention that even though, if you take epsilon over delta to infinity, the factor in front seems to make this thing explode, but that's not the case. And also it seems many people will say that this is the hardest case. Actually, it is the easiest case to address. The hardest case to address is when epsilon over delta goes to 0. But I will not comment on that. It will become more technical. Now, the point is, as I said, the intuition is correct here. You would average first. So you would fix epsilon, let's say, equal to 1, and you would take delta to 0. And then the average dynamics look like this. So there is an effective drift and an effective diffusion. This is classical averaging principle. And the effective drift is what I have denoted here by R, which basically it's again of gradient structure, but it has a factor in front, which is the one in the brackets over there, which is related to solving some Poisson equation, and people in averaging would recognize this as the cell problem, as coming from the cell problem. And then there is also an effective diffusion coefficient. And then the theorem is that the last deviations behavior of my initial model and of my effective model is basically the same. And this is on the classical form, so you get the classical form of rate functions. All right. Now, for example, in some cases you can compute things exactly because this is just with gradient flows. You can actually, the invariant measure is the Gibbs measure. You can write down the action functional in closed form. You can compute the constant that sits in front, is this k, which is essentially averages of e to the minus q and e to the q. And then you can also make observations whether the effective diffusion is slower or not. It's slower in the averaging regime. So you can have all these qualitative components if you want. Now, this could just to give you a snapshot of this. This has been developed in different directions. So we have developed this when you don't have gradient dynamics, when you have a general drift, and when you have a general diffusion, state dependent. This has been developed also when you have a system of coupled fast and slow dynamics, not just one process, when the coefficients are random fields. So when the coefficients are also random themselves. So this is more on random homogenization. And also very recently on when you have hypoellipticity. So when you have essentially the second order Langevin equation. So when you also include velocity there. Yes?
So do you do it in a general hyperelliptic setting, or
only with periodic coefficients?
Variation in the directions where you have the noise. Only in the Langevin.
Not only, so the paper that we wrote is only in the Langevin direction. Yeah, only in the Langevin, yes. So when only you have noise in the position, not in the, but you have multiple scales and the noise, yes. So I have here some slides. I decided to keep them, but I'm not going to go over in case somebody asks them. But if you ask me, I am prepared with 2 slides for each case. So let me go now to the Monte Carlo stuff. So let me skip this. So now that you have established the rate function and you know the form of it, there are different things that you can do. First of all, you can get a sense of what the exit time will be. So this is classical metastability theory, and that says that if you know the rate function, you can compute what is called the quasi-potential, which is basically nothing else but the infimum of the rate function over all trajectories and over all times. In the case of gradient flows, the quasi-potential takes a very simple form. It's 2 times the potential function, so it's in closed form. So you can compute this infimum in closed form, and then you can have an approximation to exit times. So exit times is essentially logarithmic, as people in this audience know already. Now, then you can use this to approximate tail event probabilities, which is what large deviations theory was created for in the first place, and also to devise Monte Carlo methods. So this is and the last piece is what I will focus on. So let me now go to importance sampling. This slide is the same as the previous one. The goal is to compute probability of exit or an entrance to a set or some expectation of a functional of interest. And the methodology is to introduce a free variable, that is a new measure. So instead of computing the law of large numbers of the initial thing, I compute the law of large numbers of an equivalent thing. It's under a new measure. This dp over dp bar is nothing else but the likelihood ratio when you do the change of measure, or I'm not sure what terminology is more familiar, Gizanov density, Radonico derivative, all these things mean the same thing here. And you choose this p bar in order to minimize the second moment. All right. The estimator is unbiased, so minimizing the second moment means that you minimize the variance. Now, all right, so this is obviously a variational problem. And the way that I decided to present it is as follows. First of all, I will comment on what is the asymptotically optimal choice when you don't have fast scales. So that would be the first thing that I will describe. Then I will comment on the issue that straightforward adaptation of these ideas will not work if you have multiple scales. And I will show you why it will not work. And then I will correct for this, saying what one should do in order to correct for this inconsistency, and then some simulation studies. So that's the roadmap. So let me start with classical small noise diffusion with no state dependence in the noise, which is the simplest possible case. So large deviations for this, as I said, is well known. So if you want to approximate the probability of exiting from the set, this will be exponentially small and will be e to the minus 1 over epsilon times the infimum of the rate function over all trajectories that starts at the initial point and end at the set that you want them to end. So you solve this variational problem. And now you would say, why not just solving this variational problem numerically, plug it in, get an estimate for the probability, why do you care to do Monte Carlo? The problem is that, and as I will show you, that this ignores all the prefactor information, which can be quite relevant. And large deviations, asymptotics, many problems kick in very far in the tail. So you have to go to so small events that are of practically of no interest at all in order to use this approximation. And that happens many times. So now, if you look at this object at this g that I want to compute at time t0 and x0, the initial time, initial position, if I view this as a function of initial time, initial position, then this is a solution to a Hamilton-Jacobi-Bellman equation. It's a viscosity solution to this equation. Now, so the idea now is the following. Solving this equation is a very hard thing to do. Actually, these equations have solutions for people that are more familiar with PDs, only in the viscosity sense. And even numerical algorithms, as far as I know, even though I'm not an expert in this area, but from what I understand, if you go beyond, I think, dimension 4, they really explode exponentially. So it's really not practical to try and solve this. So what was done was to say, okay, I don't really need the solution. It turns out that I don't really need the solution. I need a function that would satisfy the previous equation, but not as an equation, but as inequalities. So that will give me a sub-solution. All right. The problem with the solution that I will show you in numerical studies is that even if you can compute it, even in one dimension, that in some cases I can solve it explicitly. So I don't need any numerical algorithm. I can just plug it in. And if you use this for your change of measure, it will not work. The reason is that it has discontinuous derivatives. So it kills the simulation. I will comment on this. Whereas here I'm requiring to have a smooth C, at least C1 sub-solution. How to construct it's a different issue, and I will come back to that in the end. But if I have this, then I take the gradient of this, the derivative of this sub-solution. Sub-solution means that for every t and x, it sits below the solution. So I take the derivative of this, and I define this function, which is a feedback type of control, minus the derivative of the sub-solution, and then I use this as my change of measure. So in diffusions, when I change the measure, I change the drift. So I perturb the drift, I add an additional component, which is the blue, which is nothing else but minus the gradient of the sub-solution appropriately normalized with the diffusion constant. And then this is my new estimator, where this dp over dp bar is the corresponding Grzynov's density or likelihood ratio. And the dynamics is the same dynamics as initially, but with this extra thing. So if you do that, you have an unbiased estimator. Now, you have an unbiased estimator, you can also prove this theorem, saying that if this Q is my second moment that I want to optimize, and I take the log and I take epsilon to 0 with a minus, that sits below 2 times the value of the solution, and it sits below, and it is above the solution plus the sub-solution. Now, why this is useful? First of all, the sub-solution property says that the value of the sub-solution will be always less than the solution. If the sub-solution is equal to the solution at the initial time, then I get asymptotic optimality. If not, I have a gap, which will dictate how accurate asymptotically the algorithm is. And it also shows you that standard Monte Carlo is the worst possible case, because that corresponds to taking the 0 sub-solution, which has the hugest gap. So the goal is to find sub-solutions that are smooth enough, and smoothness is important because what enters in the algorithm is the gradient of that function. So if that function doesn't have a continuous derivative, and if the paths enter in the space that the derivative is not continuous, you get infinities, and that kills everything. So you need smoothness. That's why these sub-solutions were introduced. So you want a smooth sub-solution whose value at the origin is as close to the value of the solution as possible.
Costa, is there any reason why you really have to work at the epsilon equals 0 Jacobi equation?
No, and that will be the third part.
Versus the viscous. Okay.
Yes, and that will be the third part of the talk. Yes. No. So let me first, because before I go to that point, which is the essential point that I want to make in the end. Now, let me first say why. So this is theory, and theory is nice up to here. But this, then, when you try to move this to the multiscale setup, it will not work. It will not work because of the following reason. Let's say that you have this equation like what I have denoted by 54. You have a drift and you have a diffusion, you have these multiple scales. Let's say that you wanted to do the idea where you say, okay, let me average first, and then have an effective equation which will not have any multiple scales anymore. So I am back in the previous case, and then I apply the previous thing. Now, if you were to do the averaging, so the effective diffusion that you would get would be essentially the square root of the integral of the diffusion square. So it would be this phi over there that, again, I'm not that old to reach. You see this? So it would be the square root of the average square of the diffusion. Then my theory says that I should just take the gradient of a sub-solution, multiply it with the effective diffusion, and that will be the control that I can use to change my measure. And that should give me efficiency. Now, once you start applying this procedure and you go through the math, you realize that you have to prove something of this sort. You have to prove that the effective diffusion minus what you would think is the diffusion minus what the effective diffusion is has to be equal to 0, the integrated version. That statement in red would be true if this phi was the integral of sigma, not the square root of the integral of sigma square. So you get this inconsistency, and that is why this doesn't work, because the square of the integral is not the same as the integral of the square, basically. If you don't have multiple scales, these two things are equal, right? Because there is no y, so sigma square is equal to sigma square. But if you have the multiple scales, you have to average, and the square of the integral is not the same as the integral of the square. So this phi on top is the actual effective diffusivity, but the important sampling would require something of this sort to be true. And this can never be true, because the integral of the square is not the same as the square of the integral. And this is why mathematically this fails. So what do? You have to correct for this. And this is now where averaging theory comes in. You have to include, you should again average, and you should consider the effective Hamilton-Jacobi-Riemann equation with the true average drift and diffusion, but you should not just use the gradient of this. You should also put in the corrector information. The corrector information is essentially the second order information that you would get from expanding these solutions. For example, the first order correction is when delta is equal to 0 is, so if you can think of it as doing Taylor expansion on the PDE. You Taylor expand it with respect to delta. The first order correction is what your limit is, and then you have plus delta something. This something is the corrector. So you need to take the second order information into account. And this comes through what is called in averaging theory, in this case, corrector. So it is this chi over there. So if you do this, and G is still a solution or a sub-solution to the actual effective dynamics, then you can prove the same theorem that I had before, but with this new modified bias term, if you would like. So I have this thing in the parentheses which is modifying the previous thing. So this takes into account the prefactor information. Now, physically, this makes perfect sense, because when you do the simulation, you do it not for 0 delta or for 0 fluctuations. You have fluctuations there. So you have to take them into account, and this is the correct way to take them into account. So this this introduces a weight, and this is the appropriate weight that would give you the same theorem as before, the same optimality as before. Now, and actually in the gradient case, you can compute these things explicitly, because invariant measure is Gibbs measure. So this corrector information, which is what I have in red here, is nothing else but e to the q divided by the integral of e to the q. So it's really like a weight. And this depends on the position of the fast dynamics. Y is the fast variable, so it's x over delta. All right. Now, just some examples to show you that if you don't do it this way, you will get rubbish. So even in very simple cases like x squared in one dimension, and you want to compute this thing, with this h is x minus 1 squared. This is a rare event, because for this to be maximized, h has to be minimized, and this happens when x is 1 or minus 1. So the attractor is at 0, so you have to go against the dynamics to reach the maximum here. So this falls into the rare event stuff. And let's compare three estimators doing nothing, so just running forward the simulation, doing what was suggested before, and ignoring the local information and just doing the averaging. And people were doing this before, so there are papers that were just ignoring the local information. Now in this case, because we're in a very simple case, I can compute everything explicitly. I don't need to do any numerical analysis. So, and then you have this table. So let me go through this. These are values of epsilon, how strong the noise is. I expect that as epsilon gets smaller, the estimator of the expected value, which is theta 1 hat, will be getting smaller. As delta gets smaller, I have faster and faster oscillations, but I do it in a way that epsilon over delta gets larger. All right, so I'm consistent with my theory. Then this rho hat, so theta 1 is basically the estimator based on the scheme 1, which is with the optimal change of measure, asymptotically optimal. And then these rho's are relative errors per sample. So you get the variance, you get the standard deviation
divided by the estimator and multiply this by square root of n. N is the number of trajectories. So this is relative error per sample. So this was done in parallel, and then what you get is this. So a good algorithm should be decreasing the relative error as the event becomes more rare and should be very stable. So if you do nothing, you see that as the event becomes more rare, this explodes. So you need, on average, let's say in the last lines, you need an average 10 to the 3 more trajectories, 10 to the 3 times more trajectories to achieve the same computation efficiency. The other red thing, rho 2, is basically if you ignore the local information, in which case you still have this increase. So this is not really any good than doing nothing. It's basically of the same order of disaster. Whereas if you do it correctly, you really nail it down. So introducing this weight really nails it down. And you can do this even if this Q is a random field, which is more realistic. So this is just, I took a Gaussian random field with some smooth correlation structure. And then you can compute the probability of going at the point of the level set. Again, the same table. This dashed line means that there was no successful trajectory. So these simulations were done with 10 to the 7 trajectories, so 1 billion, I think, right? 10 to the 7 or 1 trillion, something like this. And with standard Monte Carlo, there was not a single successful one in this case. So there is no estimate. Whereas here, if you do it correctly, you get something very good. You don't get relative error 1 because you also have the approximation of the ergodic theorem due to the fact that the coefficients are random fields. So you have an additional error there that you cannot control too much. But it's very stable, whereas if you ignore the local information, it does explode. All right, so in the last, so that is why you need to adjust and use the correct information. Now, in the last 10 minutes, I want to comment on the question that I was asked before, which is one of the main things that have been working on the last year or two on this. So how to do this? So this all relies on being able to compute and to write down sub-solutions. This is actually quite hard. If you don't have state dependence, this is very easy actually. You can write down essentially affine functions that are sub-solutions and work very well, and people have done this. If you have state dependence, meaning that, state dependence, and metastability, this is not trivial. So let me comment a little bit on what are the problems and how we dealt with those and what are the open questions here. So this is a delicate task because you have state dependence and rest points. Now, and you want sub-solutions. Not any sub-solution is as good as another one. There are qualitative differences that make the difference. So for example, you want your sub-solution to force trajectories to exit the neighborhood of the attractor in a reasonable time. You don't want them to exit very fast, and there is a reason for this. You want to have some reasonable likelihood, exit of likelihood. You want a large percentage of those to reach the event of interest. You don't want rogue trajectories. Rogue trajectories are trajectories so when you do the simulation, you have the noise. And however you would try to force your trajectories, the noise would lead them inevitably to other areas of the space. That will happen, that's fine. But you want to minimize, you want your sub-solution to be such that it will be strong enough that will minimize the likelihood of those trajectories going to bad areas of the space and spending a lot of time there. So this is also not trivial to do. And you want things to be implementable in high dimensions, which means that it's not enough for me to say you solve this PD, you get something, and then you plug it in and you get your result. Because that will be, in theory it's nice, but in practice it's kind of useless. So, and also a change of measure based on following optimal paths is not optimal actually, in practice. And I have simulation studies for this, and now we know why that doesn't work, both in theory but in physical terms as well. So I will come to that. And the rest points have been usually ignored in the literature because, or gracefully avoided, as I say, because it introduces several issues. So it turns out that you need controls that also actually depend on the size of the noise. Because you do the simulation before sending epsilon to 0, right? So you have the actual noise, so you have some actual variation there, so you need to take that into account. And you want
change of measures that don't just work good asymptotically. I will present you studies where you have asymptotically optimal change of measures that do horrible job. But they are asymptotically optimal, so the theory is fine. And you want to combine both good decay rate and non-asymptotic behavior under reasonable conditions. All right. So we know how to construct subsolutions for the problem of escape of an attractor. And the issue is that if you do the pre-asymptotic analysis, you will find, and I will show you some examples, that in the pre-asymptotics of the second moment, you have an interaction between the different parameters of the problem. Like epsilon is the noise, but capital T is the time of simulation. So, for example, in one case that I will show you, you have a prefactor which is T over epsilon. It's e to the T over epsilon. So if the time of simulation is large, but the noise is not small enough to control for this, you have huge second moments. So essentially, it is the prefactors that are killing the simulation if you don't do it correctly. All right, so let me now go over this. So one thing that was used a lot, but the applied community had already realized that this doesn't work in practice, but they didn't know why it doesn't work in practice, is to reverse the dynamics. So or to use for people that are more familiar with large deviation theory, the quasi-potential as a change of measure, which means you just use as a control the infimum of the rate function over all times, which amounts to basically making the minus a plus, minus the potential, making this a plus. All right, so this makes the rare event totally not rare, because you just exit, everything goes upwards, and you are happy with this. Now, this doesn't work, and I discovered that I forgot to write this down. So it doesn't work, first of all, in the neighborhood of 0, because the gradient there is 0. So this introduces issues, mathematical issues. But maybe I should write it here. The point is that, because I don't have it there, the point is that if you want to have a bound, let's say, on the second moment of your estimator, this is the second moment. It turns out that doing this change of measure, you can establish a second moment, a bound from below of this sort. I don't know if that is visible. You have a pre-asymptotic bound, e to a constant that you don't really care about, and then you have t minus 1 over epsilon. So when you take the log and you take epsilon to 0, obviously this term disappears. But you have this competition here which remains in the pre-limit. And if t is large enough compared to 1 over epsilon, you get terrible stuff. And this is what happens. So this is just to show you an indication why this wouldn't work. So this is just a two-dimensional thing where you want to go from one well to another well. The particular form of the thing is not important, but these are estimators using the scheme that we wrote down, and I will explain to that. So you have over a range of probabilities from 10 to the minus 2 to 10 to the minus 11, or 10 to the minus 12. So from not rare to very rare. Now, if you do the quasi-potential, so if you just reverse the dynamics, and here I have a table with a distribution of the exit time. So different values of epsilon, strength of the noise, different values of time horizon, which means exit by time t. When time t is small, you get relative errors per sum that are quite good. So it works very reasonably. But as long as t starts getting larger and larger, you get very bad relative errors. The reason is that the mathematical reason is here. T is not strong enough to compete with, or let's say epsilon is not strong enough to compete with 1 over t. So, and even if, you see, in these values at the end of the table, the event was really rare. It was 10 to the minus 12. Maybe if I go to 10 to the minus 30, it would be fine, but then it would be of no practical interest at all. Just 1 minute and I'm done. So, let me just tell you what we did here. So what we did is that we realized that if you are near the equilibrium, the dynamics are basically linear, because you can linearize there. So you have a linear quadratic regulator, an optimal control problem, which is a linear quadratic regulator, which you can solve actually explicitly. And the solution to the Hamilton-Jacobi-Bellman equation looks like this. So you have these exponential curves, below of which you can approximate the solution. We have some error there because of the approximation, but these are really exponential curves. So they open up in the end, but in the beginning they are fine. in the very big, in actually quite a lot of space, where you can rely on solving this quadratic regulator, and outside of this you can actually use the quasi-potential, and that works perfectly fine, but it has to be outside this critical area. And this critical area depends on the size of the noise, and it has to depend because noise is there. It's not that you can kill it. So, and in the previous scheme, in the previous exactly example, these are the relative errors that you get if you do it the right way. So you get the relative errors that are really optimal. They're like 1 or 2. So you really nail it down. And this is if you do it solving the actual Hamilton-Jacobi-Bellman equation, so using essentially the most likely paths. This is just a picture with a size of the noise that was very rare. The event was 10 to the minus 13. No, 10 to the minus 3, I think, and 10 to the minus 13 here. The black one is the one that is asymptotically truly optimal, meaning most likely rare event trajectory, and the red one with what we did. So the black one, you see that the relative errors explode after some time, and the reason is that even though it is asymptotically optimal, you have discontinuity in the derivatives, and actually you don't have one optimal path. The discontinuity of the derivatives means that you have multiple optimal paths. So even if you try to follow one of them, trajectories, the noise will take you anywhere they want. And now that is ongoing and finishing work, we have generalized this to SPDs with a postdoc at BU. So we can now move this theory and the subsolution theory to SPDs, and these are some numerical results for exiting from L2 balls and the relative error. So it can work even in high dimensions as soon as you can identify a manifold that the rare event takes place, a lower dimensional manifold. And in some cases you can do it, and we are working on this. It's more or less done. Anyway, so I know that it took 2 minutes. So I'm done. So these are some just conclusions. I don't think, maybe the last one, especially if you have multiple scales, important sampling is important because the cost of simulation of a single trajectory is very high. So if you need a small number of trajectories to do the same job, it's very important because it takes a lot of time to simulate trajectories when you have multiple scales and noise. Yeah, so here one open question is how to devise numerical schemes to accelerate the simulation of these multiple scale SDs. There are numerical schemes that do it, but the problem is that you need really time scale separation to apply those. There are people that are experts here. But here you have also the epsilon, the noise. And what I discovered is that if I apply these techniques, I need to go to so small values of delta of the fast oscillation that imply so small values of epsilon that the event is so rare that is of no interest. So there is a gap there in the literature that I don't know how to address.
Move on to questions.
And I am done. Thank you very much. Thank you.
Are there any questions?
Yeah, the references, so there are some classical books on averaging, and then I have here the paper by Zvancic that I mentioned in the very beginning that actually motivated some of this work. And then the papers that I wrote with Dupuy and myself on different aspects of this. Yes.
Yes.
So I was wondering why you are not, for example, using the WKB approach to get, for example, the prefactor. You get here the exponential of phi divided by epsilon, but we know that the prefactor also depends on epsilon. Now, you can use WKB, and you have the Hamilton-Jacobi equation, and then you can use the technique, the standard technique. Why are you not using this to get the exact asymptotic?
First of all, no, I understand. I know what WKB is. First of all, you can view this corrector theory as a rigorous way to do WKB. WKB is what? You basically scale with e to the minus the solution, and then you write a PDE for what remains, and you expand this with respect to epsilon, and you match the different terms of epsilon, and then that is your expansion, right? Now, the corrector theory in theory of averaging is doing this in a rigorous way. So basically, if you want, in simple terms,
in WKB, you get a transport equation that you don't get in all of what you have described here. And the transport equation give you the additional term that you are missing here.
No, we're not missing anything. We get...
You take the log of the probability.
Yes, I know this, but wait.
So the term that I'm talking is usually by taking this. You don't get this term. You kill it by the log.
You kill it by the log, but you can do the expansion either with the log or without the log. Stochastic control people have done it in either way. You can do it either taking the log or without taking the log. And these two things are transformable from one to another. So you can do it one way, you can do it the other way. These are equivalent things. But WKB is not valid for any PDE. It's a very useful heuristic method. Here we did it in a rigorous way. And actually, in many cases, they are equivalent. They are identical because one is transformation of the other when they both work. So this is, I think, the best answer they can give to this.
I think we need coffee. So we will reconvene at 11.
Yes.
Thank you.
Thank you.